All right, so when we explored regular homogeneous tessellations, which was two-dimensional work, we talked about which regular polygons could be used to tessellate the plane. We found triangles, squares, and regular hexagons worked. Recall that I told you to stay tuned about those regular pentagons that came together with a gap, because that gap is what is required to create a pop-up corner. So we're going to take a look today at how many different regular polyhedra we can make. Three-dimensional shapes using just one type of regular polygon where every vertex at which they come together is equivalent. So we'll be organized and start with triangles and work our way up through the polygons. So note that we need at least three shapes to come together to form a corner. So if we start with three triangles, we fold them up together, you're going to have three triangles coming together at each corner. We could continue that around the whole shape, and what we come up with is this shape. Notice the three come together at each corner, and it takes four triangles to complete this shape, so we call this a tetrahedron. Okay, moving forward, we could try four triangles. Notice we still have a gap so that we can fold it up and pop it into a 3D corner. Right, so you're going to have four triangles coming together at each corner. If we continued that work, we would get this shape, which has four triangles at each corner coming together. It takes 8 triangles to complete this, so this is called an octahedron. Moving forward, we can still use 5 triangles and have a gap, so we can pop up that into a corner. Notice it's going to be a little flatter, so it's going to make a bigger shape when we get done. So what we're going to do here is continue that all the way around, and we're going to end up with this shape. Again, 5 triangles coming together at each vertex. This is called an icosahedron. Okay. If we tried to put 6 triangles together, remember that that's what we found would make a tessellation, so it's flat, so that is not a 3D shape. So we're finished with triangles with just those 3 solutions. Moving on to the next polygon that we know, the regular polygon would be squares. And again, we need 3 to come together to make a corner. So if we pop these up and stick them together, we're going to have this shape happening here, which you'll recognize that will come together to make a cube. And again, this would have 6 sides. We know that about cubes. So one way to name this would be hexahedron, and then we also have this specialized name cube for that. All right, and if we put 4 squares together, notice that we get the flat tessellation, which means we're done talking about squares. So we had 3 solutions with triangles, 1 solution with squares. All right, now here comes those pentagons that I told you about. So we've got 3 pentagons to make a corner, and as I pop them up, you see that they start to make a corner. All right, and if we continue doing that all the way around, we get this shape. Looks a little bit like a soccer ball. Okay, 3 pentagons coming together over and over again, all around the shape. This is called a dodecahedron. Do meaning duo, dec meaning 10, so 2 plus 10, 12. It is a 12-sided figure. Okay, and that's pentagons. If we added another pentagon, there'd be no gap anymore, so we can't go further with pentagons. Our next shape would be hexagons. But notice, as soon as we put 3 hexagons together, which is how many we'd need to make a corner, we've got no gap, and therefore this would tessellate and stay flat. It would not give us a 3-dimensional shape. So is that amazing? Now we have all of the possibilities covered already, and we've only got 5. So we've got the tetrahedron, the octahedron, the icosahedron, the cube, and the dodecahedron. Okay? And if you, like me, are somebody who has someone in your life that plays D&D, you will recognize these as the dice that they use for D&D. The D4, the D6, the D8, the D12, and the D20, named after how many sides each of these have. All right, and these are dice because they have an equal chance of landing on any of the given faces because they are homogeneous all the way around. Everywhere you look, from any angle, these have the same shape. So that's how we discover all 5 Platonic solids, and there are no more.